Well, good afternoon. It's 12:24, so I'm running a little late, but I had a student come by for advising and a phone call all during lunch, and I only had less than an hour for lunch, so I was a little late getting here. Nobody was in the room, so I went down and rinsed my hands off and tried to clear my head. As you can tell, I didn't do a great job of that, but it's better than it was. But anyway, it's supposed to be Cal 3. On Monday afternoon, the 16th of October, 2017. Just a couple of announcements first. Obviously, I've got the not my computer back, but I have a computer that they loaded Screencast-O-Matic so I can start recording again, which I started this morning. It's not my full-time computer yet. It's just a loaner from the IT department, and but it's working fine. A couple things it's doing differently from the other one, but I can live with them. Okay. Number 2. This is usually sometime this week they will open up what they call midterm progress reports, which indicates students who have D's or F's at midterms that we want to try to find out what's going wrong and do anything we can to help. So that should be happening this week. So try to get something into me, a paper. I was going to give out the test today. I didn't expect those back this week, but nobody's here to take the test unless someone else comes in later. So there's that. So I think that's all for today. Oh, my office hours on Mondays and Wednesdays are now like they used to be. I think they're going to be set pretty much this way for the rest of the term, 3:15 to 5:15. Well, with one exception. Wednesday, I've got to go to the Birmingham campus right after 3:15 to be there for a meeting at 4. I'll be there 4 to 5, and I'll just stay and work there the rest of the afternoon. So I have office hours today, 3:15 to 5:15, and probably will be here later. But this Wednesday, I will have to leave as soon as my 3:15 class is over with so I can go to the Birmingham campus. All right, Tuesday and Thursday, here's the big change. First mini-term physical science is over. It started at 1:15, which meant I only had office hours from 12:15 to 1:15 on Tuesday and Thursday. It was also my lunch hour, but that was the only time I was in the office between 8 o'clock in the morning and 5:45 in the evening. So that has changed with the second mini-term. Second mini-term, I'm teaching Physical Science 2, which the automotive students take, and in fact, that's the only reason I offer it on the mini-term, is because they need it on the mini-term, and those that will be taking it are in a class, automotive class, up until 3 o'clock, so I can't start their class until 3:15, which means now I have office hours from 1:15 to 3:15 on Tuesdays and Thursdays. Now tomorrow will be a little change. The student said he was coming by at 12:15 for advising. That's the one that came by today. And if that's the case, if he does come by at 12:15 tomorrow, sorry, my throat is so bad. If he does come by at 12:15, then I'll deal with him first, then I'll eat lunch, and then I'll have office hours. So it may not be exactly 1:15 to 3:15 tomorrow. But on most Tuesdays and Thursdays, that'll be the case. The bad news on that is that I'm here till 8 o'clock at night rather than 6 o'clock like I was first mini-term. But that gives me 2 more hours of office hours on Tuesday and Thursday than I had before. Fridays are still 7:45 to 11:45 on the Birmingham campus. All right. Can't think of any other announcements, so let's move on to where we left off. 13.5, this is chapter 13, Calculus and Vector Value Functions. 13.5 is motion in 3 space, and we just got started on 13.5 last time, so we're on page 722. And there's not a slide for what we're doing now, so let me go on and set up Screencast-O-Matic here. Oh, I am recording, sorry about that. this is the thing I don't care about this. Number 1, this should be closed. And number 2, this should be opened. Okay, got it. All right. Here's what I needed to do. Slideshow from current slide. All right. Now, things you might note, I don't know if you'll see this at home or not, and it's been a while since I've recorded, so one thing I think you'll note is that it looks like I'm writing bigger. It really isn't. What they've given me is a much smaller screen to write on, so of course when it expands to a full screen for your present, for what you see, the writing looks bigger. I'm writing the same size or smaller because they gave me a smaller surface, but it's a pain in the neck. All right. Earlier, we looked at how to get a velocity from a displacement vector, take it a derivative. How to get a speed from the displacement vector or the velocity vector, take the magnitude of the velocity vector. How you get acceleration vector from the displacement vector or the velocity vector, place the first derivative of the velocity vector or the second derivative of the displacement vector. Okay? Now let's go the other way. Okay? If an object's acceleration is given, but we want to get velocity, then we basically use the same principle of what we just were talking about. This is different processes to get going here. If you are given acceleration and you want to know velocity, well, you know that dv dt is equal to a, where velocity, and this is a function of t. Well, let's write that in differential form. dv is equal to a of t dt. Integrate both sides, and this gives you v of t is equal to the integral of a of t dt. So, of course, if you take a derivative of velocity to get an acceleration, you can integrate an acceleration to get a velocity. All right. Now, written in that form with an indefinite integral, if you had been given the formula for the acceleration, you would integrate that, vector integration like we did in the last chapter, okay, component by component, but then you would have a plus c for each of the components, or just a plus c vector at the end. Now, if that had been a definite integral that you knew velocities at between two certain times, then you would get a definite answer just evaluating it by the fundamental theorem of calculus part 1. If then you wanted to go from there to the displacement vector, r of t, then, well, I left off the part. V of t is equal to dr of t dt. So write that in differential form, and you get that r of t is equal to dt, v of t dt, I can't write and talk, and then you integrate both sides, and you get r of t, I'm sorry, this is dr dt is equal to v of t. Write it in differential form. dr is equal to v of t dt. Integrate both sides. You get r of t is equal to the integral of v of t dt. That's what I was trying to get to. Now this time they wrote it as a definite integral going from 0 to some value t. Now they usually don't do that. Hey, Victor, sure is good to see you. I get so bored talking to myself. Okay, as you get bored talking to me talking about it, like that. All right. Let me get projectors fixed. Lights switch. Now, I apologize for my voice. You really football game. I yelled too much. Sorry. And I guess the projectors will come on in a bit. All right. I was just giving the formulas you would obtain if you're given acceleration, you want to know velocity, or if you're given velocity, you want to know displacement. Okay? Because acceleration is first root of velocity, so velocity is the integration of acceleration, and same thing. Velocity is the first root of the displacement, and the displacement then would be the integral of the velocity. Now they wrote this one as an indefinite integral. In that case, you have the plus c, and the plus c, if you had initial conditions, you could calculate and find out what the constant is. The second one, they wrote it as a definite integral, but with a variable as the upper. And most of the time, they don't do that. They would change this variable to be tau or something else other than t, because it looks rather weird having a t here, and a t there. You're integrating with respect to t, evaluating at t, it just makes, it's just a little sloppy notation, but that's how they wrote it, so we'll live with it. But that's getting to example 2, and pretty easy example, I think you'll find. Let me clear the screen. Okay, and example 2 is finding R of t. What we're looking for is R of t, given that A of t is equal to 2I plus 12tj, V of 0 is equal to 7I, and R of 0 is equal to 2I plus 9k. Now, just a little bit of a timeout here. What we're looking for is R at any time t, the displacement vector at any time t. Given only the acceleration vector, which I left off the, I don't write bold, so I have to put my symbols in. Okay? The acceleration vector. Given here as a vector that has t dependence, that's why it says t, and just on my notation here, if you haven't picked up on this already, when I'm writing any old vector, I put an arrow over it. However, if it happens to be a unit vector, I usually try to cap them with a caret or whatever that is called, and that indicates that's a unit vector. So this is a not necessarily a unit vector, not necessarily a unit, definitely not a unit vector. These are a unit vector. E was probably not, definitely not a unit vector. I, of course, is a unit vector. R of 0, not necessarily. In fact, definitely not a unit vector. I and K are both unit vectors. Just to give you an idea of what we got. Okay, what would be your first step to go to find R given that A and those initial conditions?
You said define R.
Yeah, and you can't do it in one step, so don't try to get there in one step. Take as many steps as you need.
Plug in.
Second?
Plug in.
Plug in where? Okay. Let me back up a slide. If you can read my chicken scratch here. Whoa. That's right, I erased my chicken scratch. Sorry. But you can almost see it here. We're looking for R of t. This is, if you knew R of t, take it through, that gives you V of t. Take the magnitude of V of t, that gives you the speed. This is vector V of t, this is scalar V of t. take this velocity vector, take the derivative of that, that gives you acceleration, or take the second derivative of this. So, if you were given this, and you want to get back to R, let's do it one step at a time. If you get the derivative of V is equal to A, how do you find A? If you're given A, how do you find V? If you take, say again?
You said if you're given A, how do you find B?
Right, okay. If you were given V, how you get to A is take a derivative. If you're given A, how do you get back to V? Well, under differentiation. The integral, exactly. So what we're going to do first is integrate A. Well, actually, this may be helpful. Rewrite that as dV dt is equal to 2I plus 12t j. Okay? Write that as a differential. dV is equal to 2I plus 12j till 12tj dt. I mean, what it looks like you did was multiply both sides by dt, which is kind of like what you did, but they like to just call that writing it in differential form. Okay. Then integrate both of these. Okay? And you can put that in parentheses if you want to. Doesn't matter. The integral of dv, the integral of the derivative, is the function v as a function of t. What's the integral of 2I with respect to t? Integral of 2. Hi, no. It's antiderivative of 2 dt. You bump your exponent up by 1 and divide by that. Huh? Not t squared, t. This would be 2t I, and then this one would be, bump that up by 1, that would be a 2, and divide by 2, that would be 6t squared j. Right? Because if you take the derivative of this, you should get acceleration. Okay? Right? Take the derivative of 2t, you get 2I. Derivative of this will be 12t j. But you need a plus c here. Okay? And that c is more than likely going to be a vector. So maybe I should have gone and write it as a vector, but let's just leave it for now. Now, our first initial condition here says that v of 0 is equal to 7I. Okay, I hope I copied it right. Yeah. Goodness, my eyes are stinging. So let's put in a v. V of 0 would be, plug t in for t equals 0 in here, that would give you 0I plus 0j plus c. Well, I'm sorry, we don't need, yeah, plus c. So v of 0 is 7I, right? Is equal to 0 plus 0, that's equal to c. So go back to your expression here, and this would be 2ti plus 6t squared j plus 7I, because that's what c is, plus 7I. All right, we can clean that up a little bit by making it 2t plus 7I plus 6t squared j. All right, so that's your velocity vector at any time t. Velocity vector. But what it asked for was the displacement vector. How do we get displacement vector from a velocity vector? If you get the velocity vector from taking the derivative of the displacement vector, how would you get the... integrate. Yeah, the inverse operation would be integration. So, I'm out of room. So it's okay for me to erase some of this? Okay. Let me know. Okay. This is the button I meant to push. Okay. You can't see that. You are? Okay. We've already used this, so I'm going to erase this. Okay. I'll erase this. We've already used it. I'll save that because we may need it. We do all need it. Okay. Oh, goodness, my head's clogging up. It does this, it seems like, sometimes late morning, but more often in the afternoon. I think it's a combination of the cold room, because my 8 o'clock class, big class, and they usually don't turn on the ventilation until 8 o'clock anyway, so you haven't gotten, and then lots of people in here, it stays warm. Then a 9:30 class, there's only 2 people usually in here, and so sometimes it chills off too much, and it did a little bit today, but my head didn't clog up. But then this afternoon, goodness, well, I drank some tea right before I came to, so that probably chilled me some too. Probably didn't drink enough of it though. All right, so here we have V of t, which is this expression over here. Oh, I erased too much, didn't I? Yeah, let me rewrite this part. 2t plus 7 I plus 6t squared j. No k component yet. So that's your V of t. I want to rewrite that V of t as dr dt. That is what your velocity is your rate of change, time rate of change of your displacement. So that's going to be 2t plus 7I plus 6t squared j. Okay. Now what I'm going to do is write it in differential form, bring my dt over there, and integrate both sides. I think I'm going to have to go up here to the top. And the integral of a derivative is the function itself. So this is going to be your r of t at any time t. And we're integrating 2ti plus 6t squared j. Let's do that one first. How does that integrate? 2t plus 7i. Two. No, actually the 2's cancel out. Remember, integration is the reverse operation of differentiation. What it sounds like to me you just did, you took the derivative of this. We're wanting the antiderivative of this. What would that be?
T squared.
T squared, exactly. Okay. T squared. How about the antiderivative of 7? plus 7t, and that will be your I component, plus it doesn't hurt to write down the 6. That's just a constant. And then with the variable, you're going to increase it by the exponent by 1, making it 3, and then divide by that 3. And that will make this 2. So it's 2t cubed j. Okay? So there is your displacement vector at any time t. Okay? Plus c. Indefinite integral. So you have to put a plus c out here. Which, by the way, is a vector also. So I could go on and put an arrow over. I didn't on the last one, but I should have. But we also know, goodness gracious, that r of 0 is equal to 2i plus 9k. So r of 0 is equal to, this would be 0i plus 0j plus so this comes out 0i, and this would be plus 0j plus c. But we already know that r of 0 is 2i plus 9k, and that's equal to c. Remember, that's a vector. So what we can do now is plug that c in here, and again I'm running rapidly out of room, so let me erase what I can. We've already dealt with this and with that. I probably should have come up with a new variable, new parameter c, because we already used c before and we shouldn't use it again. But this is what your r of t is now equal to. Goodness, my pen won't pick up. I'm so sorry. You got on a jacket, smart, or is it a long sleeve shirt? That's pretty smart. I didn't even bring one today. It's when the weather gets cooler outside, the air conditioners really work well. Not before. Okay. So we have this as c. So now we go back to our r of t. R of t at any time t is going to be t squared plus 7t. We would put an I, but you also have a plus 2i here. So all that's multiplied by I. We didn't add anything new in j here. It was just I and k. So we'll leave our j's alone at plus 2 t cubed j, and then plus 9k. And where that came from was from our initial condition here. Our c was equal to 2i plus 9k. So you put that in up here where c was, and the I part comes up here with t squared plus 7ti plus, or was it plus 2I? So all this was 2I plus 2 times t cubed, nothing you added here, k, plus c. The c has this I component and that k component, like we saw there. So there is our displacement function as a function of time. Let's see if we agree with the book. T squared plus 7t plus 2I plus 2t cubed j plus 9k. All right. Okay, I don't think they have anything for example 3 either. Trying to see where the next slide comes from. Just going to do it quickly here. All right, I'm going to pause for just a minute. I think I've got to go get something to drink. Hold on. And I was looking for the next slide and I couldn't find it. So let's do the next example. We just did example 2. And by the way, I'm recording again. That's something I forgot to say at the beginning of class. I got a loaner computer from the IT folks, and they loaded Screencast-O-Matic on it. The one I was using from the library only had the 10-minute version, the cheap, free version of Screencast-O-Matic, and I couldn't just keep doing 10-minute segments. It would have taken forever, and so much class time. So we got back to that. The disadvantage is I've got a very small screen here to write on, and even though my writing is probably smaller than it was before, it's expanded to that and makes it look bigger, so I can't get as much on the screen. So that was example 2, and you can pick that up next time. I mean, when you go look at the YouTube video. But let's do example 3. All right, to go on and erase it. I know you just got here, but yeah. I keep hitting the wrong keys here. All right. So let's do example 3. Again, we're looking for R of t. Okay, this is what we're looking for. Find R of t. If A of t, goodness gracious, yeah. There's another thing I'm dealing with here. I had one of the busiest weekends I can remember. It was just nonstop, including yesterday afternoon. We had to left at 1 o'clock to go to Atlanta, and was that a thing that lasted several hours, and drove back last night, so I didn't get to bed before 12:30, so I'm a little wacko right now, and got up at 5:15, so I'm running near empty on sleep, and so that's probably contributing to the rest of it. Given that R of t, if A of t, this is what I've been meant to do before, is equal to cosine t I plus E of tj, e to the tj, plus tk. Okay, and just to remind you, called vector earlier. The arrow over it means it's any kind of vector, not necessarily unit vector. If it doesn't have anything like that, these are scalar functions. Cosine t, e to the t, and t. Those are just scalar functions. This, though, is there, that's the scalar function that determines the I component, that's one that determines the j component, that is the k component. So, these are unit vectors in the ijk direction. And I'll put the little hat over those so you can remind me and you those are unit vectors. Okay. So, how do we get to, okay, they give us something else. Also, they give us that v, the velocity vector at time t equals 0 is I, and that the displacement at time t equals 0 is k. All right. Now, they gave us what a of t was. Remember what acceleration is? It's the derivative of the velocity. Okay? And they gave us that was cosine ti plus e to the t j plus t, I say t and write k, tk. All right. Well, just like we did before, next thing I'm going to do is write this in differential notation. Because I have so little room, I'm just going to wipe out the dt here and write it over here. It looks like we multiply both sides by tt, and you can think of it that way if you want to, but technically we wrote it in differential form. Now we're going to integrate both sides, so integrate this and integrate that, and this is everything inside of here. Well, you integrate a derivative and you get the function, which is v of t. Okay? Now we're not really looking for v of t, we're looking for r of t, but you got to go through v of t to get to it. Okay? So your v of t is antiderivative of cosine t. Sine t. Okay? That's sine t I. Antiderivative of e to the t. E to the tj. I love e to the t. Okay? Plus antiderivative of t. Let me clean that t up a little bit. It's got some extra trash with it. Ah! Okay. Antiderivative of t. T squared over 2. And that will be your k component. And then we need, because it's an indefinite integral, a plus c. Remember, c is also a vector. Okay? You don't have to write it as a vector, but it doesn't hurt to. Now, they also told us that v of 0 was I. Okay? So let's plug in here v of 0 is equal to, what is sine of 0? Now, cosine of 0 is 1, sine of 0 is 0. So this will be 0i plus what's e to the 0. Say again? No, that's the inverse function of the exponential function. It's a log function. But what is, goodness, my hands are cold. E to the 1. Everything to the 0th power is 1. Okay? So this will be plus j plus, and then you plug in a 0 for t there, you get 0. So that gives you c. Okay? But we know this V of 0 is I. So this is supposed to be I. So obviously, C is equal to I minus J. Because you subtract J from each side. V of 0 is I. This is what V of 0 is. When you plug in 0, 0, you get J plus C. That's equal to I. So C would then be I minus J. Okay? So that gives you your constant. Go back and plug that in your V of t function here, and you get V of t is equal to sine t I. Nope. Sorry. Your C has an I component. Its coefficient is just 1, so this would be sine t plus 1 I plus e to the t minus 1 j plus t squared over 2 k. All right. My eyes are going blurry again. All right. Just refresh ourselves. When you plug in t equals 0, that goes to 0. You get I. Good. So, v of 0 is equal to I. You plug in t equals 0 here, you get 1. 1 minus 1 is 0. It has a 0 j component. Plug in a 0, you get 0 k. So yeah, that works out well. So there's your velocity function. Okay. All right. I'm going to take this and erase this part here, because I just don't have enough room to write. We already used it, we evaluated it, we did everything we could with it. And I want to leave, I don't need this one anymore, because I already wrote it down here also. And I don't think I need this anymore either, because I've already calculated that. Okay, more Treddy here. Perfect attendance today. It's good to see. And I forgot to put Jasmine here when she came in, because she came in while I was out, so I didn't put her in. Sorry. But we got everybody here. Way to go. We're on Chapter 13, Calculus of Vector Value Functions, 13.5, Motion in 3 Space. And we're just beginning to do this. This is our third example, second one we've done today with this. I haven't quite finished yet. It's example 3, bottom of page 722, top of 723. Okay. Seems like I thought of something when you came in that I needed to either go back and reiterate. Oh, I guess I know. I'm recording again. I don't have my computer back, but the IT folks gave me, they said he thought he'd have it ready by Friday. It wasn't. So he found another computer and he loaded not everything I needed, but everything I needed to do my classes on here. I've had to set it up this morning. But now that I've got it set up and running, it's going to be recording like it did before. So that meant even before Victor came in, I went on and started recording. And then he came in, and then Jasmine came in, and now you go in. So you will be able Sorry. You will be able to go back and pick up anything that you may have missed before you got here. That blank period in there the last couple of weeks when I couldn't record, I left the recordings from the last time I taught this course, which was either last summer or last spring, out there so you can follow along the sections. Well, me that I'm talking to y'all, but I was talking to somebody, and we did the example pretty much like we're doing up here. And also, before you leave today, let me give you a test on the last section in chapter 12, last section, quadrant surfaces, whatever section that was, 12:6 or something like that, and then 13:1, 2, 3, 4, and 5. So 6 sections from these 2 chapters. And the other thing is, my office hours, Monday, Wednesday stay the same, 3:15 to 5:15, with one exception. This coming Wednesday, day after tomorrow, I've got to go to a meeting on the Birmingham campus. I'll have to leave here at 3:15 to get there before the meeting starts at 4. So I don't have a lot of time there. But other than Wednesday, it should be 3:15 to 5:15 on Monday, Wednesday. But the good news is on Tuesday, Thursday, my office hours got bigger. Freshman term, I had a physical science class that started at 1:15, so my only office hours that day were 12:15 to 1:15, which is also my lunch hour. So I was in the office then. That's the only time I was in the office between 8 in the morning and 5:45 in the afternoon. So it wasn't at that time. But the second mini-term, Physical Science 2, some of the automotive students take, they do co-op, the second year students do co-op the first 8 weeks, and then they come to class the next 8 weeks. Well, they've got automotive classes that go up until 3 o'clock on Tuesday, Thursday, so they don't come to the academic side until after 3. So I scheduled their class at 3:15, and we'll go 3:15 to 5:45 class, or 5:45 to 7:45 lab, which means I get to go home about 8 o'clock, But that does give me office hours from 1:15 to 3:15 on Tuesday, Thursday that I didn't have before. And then Fridays, it's 7:45 to 11:45. Okay. All right. So this is where we left off. We started with the acceleration vector and our initial conditions. We did the integration to get to our velocity vector with the initial condition put in there, and we got this. But we're looking for the displacement vector. Well, what is velocity? Velocity, get my pen back. The velocity vector v of t is the derivative of the displacement vector dv dt, okay? And that is our sine t plus 1 I plus e to the t minus 1 j plus t squared over 2k. All right. I know my eyes are. All right. What do we do with that? We're trying to get r out of that. Right. Look. No, not magnitude. R vector. R of t. We write it in differential form, like the dt over here, if I can get it written in there, and then integrate both sides. Okay? We'll integrate everything in there. And the integral of the derivative is the function, r of t, what we're looking for. Now you help me integrate sine t plus 1. It's the antiderivative of that. With a minus sign. Minus cosine t plus t, that will be our I component, say again?
E raised to the t.
E to the t, I can't write.
Minus t.
Okay, j.
Okay.
Oh yeah, I'm sorry, yeah, we're integrating, sorry about that. Let me space it out a little bit better. Plus e to the t minus t, j, plus
and
1 over 6 t cubed k. Okay? Plus some arbitrary constant vector c. Because that was an integral. Okay? But we do have an initial condition right up there. R of 0 is equal to k. So let's plug in our R of 0. What is R of 0? Is k. Well, let me write it down. R of 0 is equal to, and what is cosine of 0? 1. So that'll be a minus 1 plus 0 I plus say again?
Oh, 1.
1. Okay. 1 minus 0. So that will just be j.
Plus 1 over 6.
No, you got multiplied by 0.
Oh, yeah, that's right.
So there is no k yet, plus c. Okay? And c being a vector. Okay? You don't really need this parentheses here, so let's take it out. All right. But we know what R of 0 is k. So this stuff is equal to k. Well, we can solve for c again. I probably should have used a different letter because we used c before, but since I erased it, I used c again. Sorry. So c would be k minus or plus I minus j. Right? You add, solve for c, add I to both sides, subtract j from both sides. You already had a k there. So let me clean that up and get it in the right order. That would be I minus j plus k. Okay. All right. Find R of t. I think we, oh wait, yeah, that's what we got to do then. R of t is equal to minus cosine t plus t plus plus 1. That's all times I, because you see has just the one I component. Okay? Plus e to the t minus t minus 1 j plus 1/6 t cubed plus 1 k. Okay. Let's see, make sure I have it. Okay. Here's my answer. I'm having trouble finding it when I look at the page. So your R of t is minus cosine t plus 1 I plus e to the t minus 1 j. For some reason I didn't put my hat over it. Okay. Plus 1, or t cubed over 6 plus 1 k. Got it. Okay. I'm having trouble talking. Now I think maybe this slide comes into play here. It may not. It's so dim up here I can't see these easily. Yeah. Not really, but close. Near the surface of the Earth. What does that mean? Within a few miles of the surface of the Earth. Gravity imparts an acceleration of negative 9.8 meters per second squared in the z equal j direction. If the units are in feet, then the gravity acceleration is negative 9.8 meters per second squared in the SI system and negative 32 feet per second squared in the U.S. customary system. This means that if we are having a projectile moving my throat hurts so badly. Near the surface of the Earth that has no additional means of acquiring acceleration. In other words, it's just a projectile. A basketball, a golf ball, anything that's been tossed, a bullet thing. Not a missile. Most missiles have a fuel source, so therefore they're accelerating themselves. They're not operating under just the acceleration due to gravity. This also, this also means that we're neglecting air resistance. Now, if this is a big, bulky object, you can't ignore air resistance. Even if it's a fairly streamlined object, if it's going very fast, you can't ignore air resistance. But if it's a fairly streamlined object and going at a relatively low rate of speed, yeah, you can pretty much say, well, we'll ignore air resistance for now. But once you get up fast enough that you can't ignore that, and that was the other thing, you have to be going slowly enough to, I think I said that the other way. Okay. Excuse me. This means we know that projectile stays in a vertical plane, and we assume that it is above the x-axis, so the entire problem occurs in the xy plane, which is very helpful. We can now take the vertical dimension to be the direction of the y-axis and take the acceleration vector to be a of t is equal to minus 9.8 j. Now, if you were in two space, just in the plane, and that's what they're talking about. If you've only got motion in two space, well, no, I'm sorry, up above, if you're in three space, usually they let the k component be represented, the acceleration, minus 9.8 k. If you're in the plane and you only have two dimensions, usually it's x and y, then the j component is usually in the y direction, minus 9.8 j. But notice in both cases, it's always given negative, because our coordinate system, positive that way, positive this way, and if that's the case, right-hand rule will be positive out of the board. Okay. Or if you did That way X and this way Y, Z would be up in the void. Z would, Y would be going into the void. Okay. Now, they mention this only in terms of acceleration. The slide here is talking about it in terms of forces. The force as a function of displacement is equal to m times the acceleration. The acceleration second derivative of the displacement. So alpha bar of t is equal to m times r prime. Times r prime. Double prime of t. Understanding that you're going to have some constants for acceleration and stuff in there anyway. Okay. So I think we're ready for example 4, which they did provide a picture. Let's take a look at it first. Goodness, this is sort of aggravating. The cursor goes behind the thing and I can't see where it's going. Let's do it this way. I like using the pad, but this computer doesn't allow it. Like I said, this was a loaner, which I appreciate, but it's a lot more awkward to use. So here's the setup for example 4. Sorry. A bullet is fired from the ground at an angle of 60 degrees above the horizontal, above the horizon, horizontal. What initial speed, v0, must the bullet have in order to hit a point I can't take this problem at all in some respect, okay? Bullet fired from the ground, okay. What initial speed, v0, must the bullet have in order to hit a point 150 meters high on a tower located 250 meters away? Of course, we're going to ignore air resistance, okay? So, they've drawn the picture for you. Thank you very much. But, on test, I'm not drawing the picture for you. You're probably going to have to do this yourself. I just returned the test, showed you how to test in Calc 2 class. And he started out his problem just entering on the computer on a graphing calculator and finding the endpoints there. He got his endpoints wrong, he got the problem wrong. Be careful with your drawings and things like this. Try to get them as precise as possible. Okay, so you fire this bullet and you're looking for initial velocity. You're firing at 60 degrees above the horizontal, and you want it to hit a point 250 meters away to 150. No, I'm sorry. Are these meters or feet? Meters, okay, we're back in the metric system. Okay, meters away. In order to hit a point 150 meters high, so that's the Y component, and 250 meters from the place of shooting. Okay? Now, because of their drawing here, the way they've drawn this, it doesn't look like any way this bullet could hit that point on the way up. And this is part of that. Your horizontal displacement is greater than your vertical displacement. Now, if they were equal, you still couldn't have hit it, and you had an angle less than 60, like 45, you still wouldn't hit it. You have to hit it on this way down. Okay? if you're shooting at an angle of 30 degrees, yes, you could get that on the way up and that same height on the way down, but it would be a lot further here. So this basically is telling you, with the x being greater than the y, the only way you can do this is on the way down. Now, you can sort of look at the picture and guess that's the case, but I'm telling you, it has no choice but to be the case. Okay? Basically, because the tangent of 60 degrees is not 150 over 250. Okay? Tangent of 45 is 1. Tangent of 60 is greater than 1. So you could not have that on the way up, because then that would have been 150 over 200 would be on the way up. This is on its way down, you could at that point. Okay. So, and we're going to ignore air resistance. Thank you very much. Okay. Did I already blow this up? I probably didn't, did I? No, I did. Okay. I need to write it now, though. Right on the screen. So, what is our procedure? Say again?
Oh, you go ahead.
No, what were you going to say?
I was just going to say know the function of B0 is.
Okay. That's what we're looking for. What is the initial speed, V0? So this is so tiny here. This is our unknown here, V0. That's what we're looking for. Okay? See, I can't write on the screen when it's expanded, so I'm stuck here. So the V0 is what we're looking for. All right. Bullets fired. We don't know the initial speed, but we know the initial angle. We're looking for that initial speed. And we know the point it's got to hit, which is on the x, in the x direction, 250 meters away. On the y direction, 150 meters high. Basically, from that, you know you can't hit it on this way up. Got to hit it on this way down. Okay. Now, trying to think. The only way I can think of working this problem is using physics, and all of you have had some anyway, right? Okay. If you, yeah, you do that. Okay. So, what do we know physically? I know you fired it in the air, you don't know what speed, you know what angle, and you know a point on that problem you're expecting to hit at some time later. All those are nice things, but I've left out really one of the most important. Okay? We're looking for that initial velocity, which has to do with the explosion in the bullet when you pull the trigger that fires the bullet up into the air. Okay? We don't know much about that. But once it leaves, once that explosion happens and it leaves, what's the force acting on that bullet?
Zero?
Nope. If it was zero, it would just keep going. It would never deviate. Never hit the tower.
Oh, the force. Oh, the gravity.
Gravity is pulling downhill.
Yeah.
Right? Not just downhill, straight down. Okay? So, the one part they didn't say, but you have to assume here, is that your, I'm trying to do it just on what they've given us here. We don't know anything about mass, so we won't bring force into it. We will just deal with acceleration. The acceleration in this problem at any time t is what? Yes, you do. Minus g. Acceleration due to gravity. It would be minus, and since we're measuring things in meters, this will be minus 9.8. And since we're doing vectors, that is a vector, j. Negative 9.8 j meters per second squared. Okay? That's the acceleration of the bullet, or bullet. Okay, firing from the ground. And we're going to put that firing point at the origin, and we know the angle. Okay. So there is something we know. Okay? There is something else we know in that. We know the point's going to hit, but we don't have that as a relation to time or anything else. That's almost sort of what we're trying to get to. But we'll get there in a minute. Well, this 60-degree angle, what does that give us?
A vector?
Say again?
A vector? I don't know.
It does. It places where the vector is. Okay, it's an angle between the horizontal and that initial velocity vector. Okay, they just haven't given us the magnitude of that. But if you think about it, they've given us something. And how you solve problems like this is keeping everything component-wise. That was a component in the j direction, negative j direction. This you break into I and j directions, or x and y directions. And what is your initial velocity of that vector? Okay. It has an I component and it has a j component. Okay. What are they?
The I component, I guess, 250.
No. That's a position that has nothing to do with velocity. Your initial velocity, v sub 0. And by the way, that's what we're looking for. Okay? But it's some value. And it has an I component and it has a j component. Okay? What are those components? Well, the I component let's call this V I H for horizontal. I hope that's okay. And this will be V I vertical for a vertical component. Okay? Now, looking at these vectors there, I can say, and we don't know what it is, but we know what V0 is. I mean, we know it's there. It's sitting there. So let's look at this. Look at that angle theta, 60 degrees, and we know that V sub I let's call it X and Y rather than horizontal and vertical. Okay? Okay. Okay. Let's look at the angle. The sine of 60 degrees is VIY over V0. Do they call it V0 or VI? V0. Let's call it V0. Yeah, these are V0s. I call them VI for initial, but since they're using 0, let's use 0. Okay, VI 0. Okay. Now, this implies that V0y is equal to V0 times the sine of 60 degrees. Okay. Come out. I think we know what sine of 60 degrees is, don't we?
Yeah.
What?
You do the square root of 3 over 2.
That's it, square root of 3 over 2. So rather than doing that, let's just write it as, and here I put I again, so V0 is equal to, that's the y component, let's do the x component, will be the cosine of 60 degrees. Okay? And that will be V0x over V0 okay, which implies that V0x is equal to V0 times the cosine. But what is the cosine of 60? 1/2. Okay? So here we know something. V0, which is initial component of the initial velocity, is 1/2. See, I'm sort of going in circles here. The magnitude of V0, I guess that's how I should be expressing it. 1/2 the magnitude of V0 in the I direction plus the square root of 3 over 2 times the magnitude of V0 in the Y direction, or J direction. Okay? All right. Yeah. And how they're writing that, if I don't put, I'm going to do it the same way they do. If I don't put the hat on it, I mean the arrow over it, that means it's not a vector. That's a scalar quantity. So that's how they do it, and it makes it look a little cleaner. You're saying the same thing. Without the arrow over it, that's just the magnitude of the V0. Okay. Now, oh my goodness, I'm stiff and sore. I think we've let all the information we can out of this, except using that point out there. Okay? Let's see. Bullet is fired from what initial speed must the bullet have in order to hit a point on a tower. Okay. If they had told us what time, we could use that. We can't now, so can we make up a time? I don't think so. Okay. So let's go back to this. This A of t is dv dt. That's the velocity there. Is equal to minus g j. I didn't put my vector in there. Well, because I used g as if it were a vector. So let's use g as a scalar and put the j component. Oh yeah, I put it there. There it is. Okay, sorry about that. I thought I had. I just wiped out something. I don't see what it is. probably was that. Okay. All right. So it's minus, let's go and put 9.8. J. That's the only component. So this says that V as a function of t is equal to, and by the way, we're going to write it in differential form, integrate both sides, and V of t would then be minus 9.8 t okay, plus some V 0. Well, no. Let's just call it C, plus C. Okay, just like we did before. Now, when t is equal to 0, I left off my unit vector. I did all that scratching around there and wound up. Okay, that's part of my picture here. So this is such an awkward thing to be writing on. This is in the j direction. Okay, so when you integrated that, you got that in the j direction. Okay, and then our c. Now, when t is equal to 0, the velocity is v0, that's acting in the y component. There is, so 1 half v0I is your component in the x direction, and that's your component in the y direction. Okay, and so when t is equal to 0, that's the case. And when t is equal to 0, of course, this is 0. So this c vector here actually turns out to be this vector up here, 1 half v0 in the I direction plus the square root of 3 over 2 v0 in the j direction. Okay, so that is your c. So let's go back and plug that in. Velocity as a function of time is equal to 1 half v0I plus the square root of 3 over 2 v0 minus 9.8 t in the j direction. Okay. Now, I don't think we need this anymore. This is one thing that's so frustrating here. It's so small. We don't need the sign any longer. Can't. Trying to erase this without destroying it. I think I erased too much. Okay. I don't think I need that anymore. I sure hope not. Okay. Goodness, I'm so sorry. My head hurts so badly. Put parentheses here. So that's your velocity at any time t. Okay? No, yeah, that's true. Okay. What's that? Forgotten what the question is. All right, so we need to get our displacement back, because this is identified by displacement, not by velocity, not by an acceleration, but by displacement. So we need to integrate that one more time. V of t is dr of t dt. This is equal to, that's right, v0 over 2I plus the square root of 3 over 2 v0 minus 9.8 t j. Okay? That's what your dv. So what we're going to do is multiply this by t, by dt, or other words, write it in differential form, integrate both sides. Okay? Now I need more room. All right. What can I erase? I don't think I need this anymore now because I've already used it. Hopefully I won't need that anymore. Whoops, I just erased too much. I think we're okay. I think I've got my formula, so I'll erase this one. Yeah, because all this, let's figure out what C is. Okay. Man. Seems like all the cylinders aren't hitting. Okay. In fact, I think I can live without the velocity too, so let's go on and get rid of that one as well. Because I already wrote it down below. Okay. Get rid of that too. Okay. I may not need the other either, but let's hang on to that. So when you integrate this, this gives you r of t. The integral of the derivative is that, the function, okay, r of t. Now this is equal to, what's the integral of that first part? This part right here, with respect to t. v0 over 2 you're integrating that.
And it's supposed to be 4?
Second?
And it's supposed to be V0 over 4 or?
Okay, where do we get the 4?
I don't know yet.
I don't have one up there. If my writing looks like it, it shouldn't be. It's 2. That was from the cosine of 60 degrees is 1/2.
Yeah.
Okay. But you're integrating a constant with respect to t.
Okay.
What do you get?
I guess V0 over 2.
Integrating that dt. Antiderivative of dt.
Yeah, hold on.
The antiderivative of a constant times dt. We're going to do the dt by each one of these. Huh? T, just t. Okay? Plus, and this one again, there's a constant, so that'll be square root of 3 over 2 v0 t minus, now this one, this is I. Okay, this is your integrating 9.8t, antiderivative of negative 9.8t.
It just be 9.8 t squared
over 2, which would be 4.9 t squared, right? And that's your j component. Okay. now we have a C. Okay? Now, we don't know what time it is this happens, but we know at some point out there, you have to intersect this value here, 250 on I and 150 on J. So, that's going to be your R of T at some time C. At some time T. Do we need to know what that next T is? That next constant is? Oh, yes, we do. We have an initial position. At time T equals 0, where are you? At the origin, 0, 0. So when T is equal to 0, that's the other thing I failed to, we said it, but we didn't write it down, that R of 0 is equal to 0I plus 0J. Okay, the 0 vector. You're at the origin. Okay? So when you plug that in for T equals 0, your C vector has to be 0, 0. Yeah, so you don't gain anything there. So that just gives you C is equal to 0. So that was easy. It was so easy it was almost invisible. Okay? So basically that makes the C vector 0. Because what we have there, when you put in a 0 here and a 0 there and a 0 there, you get 0I and 0J. And why does that I look like a J? Okay. All right, so your C is C1 is what they're calling it, is equal to 0. Okay. Now, as I said, this R of T at some time T, and we don't know when that time T is, that's going to be the vector 250, 150. Both of those measured in meters, and that's why we're using 9.8 meters per second squared. Okay? Now, the easiest thing to deal with here, if you know that V0 over 2 times T is equal to 250, right? Multiply both sides by 2 and you get 500 and divide by V0. So that's what time you're going to be there at T equal 500 divided by V0. Okay? Okay? Now, plug that in over here. And this component has to equal 150. So the square root of 3 over 2 V0 times 500 over V0, that's the time. Notice the sound effects, they go out. The 2 and the 500 makes that back to 250, okay? Minus 4.9 times 500 over V0 squared, because you're squaring that time. This has to equal 150. Okay, that kind of gives you a quadratic equation. And if it's all right, I'm going to go back up and erase some stuff. I don't think I need this anymore. And hopefully I don't need this anymore. I think we've already used that well up. And I'm kind of guessing we don't need this anymore either, because I think we've used that adequately. All right. maybe I'll leave the other just in case I need it. Okay? So, let's clean this up a little bit. The square root of 3, or 250 times the square root of 3, minus 4.9 times 500 over V0 squared is equal to 150. I hope that's what I've got here. I think it is. Okay? Now let's multiply. What I'm going to do now, just because I have so little room, let's square this out. Squaring 500 will be 25000. So that's 250,000, right? Okay? And this will be V0 squared. This is messy, but it's okay. I think before I do that, let me also do this. Let's subtract. Here we have 250 times the square root of 3 minus 150. Subtracting that from both sides is equal to 4.9 times 250,000 over V0 squared. Well, let's multiply both sides by V0 squared, wipe it out there, and wind up with that over here, V0 squared. Divide both sides by the 250 root 3 minus 150. Okay? I hope I can erase this now. If I can't, that means I'll never be able to find my error if I made one. Hopefully I didn't. Okay? Do I need that at the bottom as well? I don't think so. I think we've already used this. For some reason it's not erasing. There it is. This is the strangest pen. Okay. So let's see what we got. And you might want to pull out a calculator. V0 squared is equal to, you got a calculator, anybody? Have we just gone over?
Yeah.
Sorry about that. So, this is left to the student, okay? Let's see how close we are to what they've got. What we wound up with was V0, what they wound up with is V0 over 500 squared, which we wrote as V0 squared, multiplied by 500 squared, which is 250,000, times 4.9, divided by that. That's exactly what we got. Go home, punch that in on the calculator, and see what you get, okay? And I'm not sure I would do it the way they did, but it looks like we're on the right track. And we got down to the place where we'll start we'll do linear motion, circular motion next. All right. Sorry that between my throat, everything else, I was sort of wacko. So we'll begin then on 724. We only have a couple more examples to do, maybe 3. So homework exercises here, do number 1, either 3 or 5 or both. And then think you can do any of the odds 7, either 7 or 9. Either 11 or 13 or both. 7 or 9 or both, either 15 or 17 or both, and then start with some of the odds 19 through 25. If you can't get them all, hang on, we'll pick up and go from there next time. But what I wanted to do today is go on and give you, because I had hoped to finish this today, and in between my throat and everything else going on, and we got started late too, we didn't quite do it, but I wanted to go on and give you your test, because I went to have them run off, and I found out I already had enough for some reason. Now, if I can find them. I had them on top. Yes, here it is. This one looks a little worse for wear. This one doesn't look quite as bad. So that's my original. Nope, I had 2 originals, didn't I? I'm not sure why. Well, that's what messed me up. I thought that was an extra copy, and it's not. That's an original. So I do have to go make another copy. I thought for sure I had enough. Because what it said, how did I wind up with enough? Do any of you need to run? Wait. They aren't the same. So I didn't have enough copies. Which one do I want to do? Okay. Oh no, I'm looking at the wrong one. There's the third one. I hadn't gone deep enough. Okay, I have 4 copies. These are something else. I'm sorry, folks, this is just going crazy today. I think that's the one I want. Let's see. All right. Those 2 are the same. Those look, no, they're not. No, they are. Maybe all of them are the same. I think I know what happened. There's one. That's a little bit better. Okay, let me read through all the questions. You tell me if you got them right. If we got it. Write the equation of the quadratic surface, 9, blah, 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 in standard form, and identify the type of the quadratic surface. Is that your first question? Okay. Number 2, identify the quadratic surface, blah, blah, blah. Just did. X squared minus y squared minus c, blah, blah, blah. Got it? Okay. Number 3, parameterize the curve at intersection of the surfaces y squared equals z and x squared equals y. R of t is blah, 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 blah. Right? Okay. Number 4, find the point of intersection between the curve R of t is equal to cosine t squared, sine t squared, I, j, and k, and the plane z equal 5/4. Right? Okay. Find the parametric equation for the tangent line to the path R of t is equal to inverse tangent t log t e to the minus t. Right? At the point where t is equal to 1. Right? Okay. Evaluate the definite integrals. Integral from 0 to 1 to square root of 2t I plus blah, blah, blah. Right? Okay. Find the arc length of the curve R of t is equal to 3 sine t minus 1, comma, negative 3 cosine t, comma, 4t. Right? Okay. Find the length of the curve described by the vector function R of t is equal to 1/2 t, 4t to the 5/2, 25t4. Right? Okay, for a certain. Find the curvature R of t for t, 2 sine t, 2 cosine t. Right? And the acceleration vector is given 25 cosine 5t, blah, blah, blah. Is that okay? I thought my 2 originals were different, but all 3 of these were the same. Okay. All right. So please write in speed. Good deal. Thank you. Thank you. Thank you. Perfect attendance. That was great to see. In my recording, I should have ended that right into that.